Okay, so again, some students ask about whether or not this course is going to be online. I mean, as I said, I will prefer this class to be taught in person. But if the school tell me to change to online teaching, I will notify you guys. Okay, but so far we are still teaching online. Sorry, we are still teaching in class. But if because the COVID-19 situation looks like it's becoming worse, so I don't know. I don't know the future situation. I mean, if the school tell me to change this course to be online, then we will have to be that. But before that, I mean let's still stick to this way. Okay. So, okay, I mean, we talk about convex hull, right? So, but now, I mean, we are going to talk about a slightly different version of the convex hull. Okay, just like every other chapter, okay, we need to motivate this problem with a certain real world problem. So now, okay, I mean, for this chapter, we are going to discuss some. This is one of the probably most important chemical process. Okay, in the chemical engineering. Okay, because in chemical engineering, I mean, what they do about different chemicals, I mean, is that they mix things a lot, right? They are mixing many different materials together, okay, to sort of construct new from new material. Okay, so for example, they can mix different oil from different wells to produce favorable one for the refining process. Okay, because when it comes to oil refinement, okay, then this is very important. Okay, so we know some can be made, but some cannot. Okay, so I mean, normally we don't consider this problem geometrically, but we could consider this geometrically. It's like this. Suppose we mix, okay, three different materials. Okay, three different materials. Each of them, say, contains two. I mean, each of them contain two different type of content. Okay, so we have three sources. Okay, the first source. Okay, the ratio for these two materials is 0.1, 0.35. The second source is for these two different material. The ratio is 7% and 15%. The third source from I mean for these two material, I mean is 16% and 20%. Then okay, if you try to mix all, I mean the oil from these three different sources. Okay, the only possible percentage of these two materials you could possibly make can be represented by this triangle, right? Okay, and then okay, say if you generalize this idea, okay, if you have more than three sources, and each one assume you have more than two, what should I say? More than two different materials. Okay, then you can sort of represent this one into like a, you know, higher dimensional, like a stuff like this. So each point, each source will be a point in this. This is actually a polytope. Okay, 3D 的 convex hole. Okay, in English we call it polytope. Okay, convex polytope, and each vertex actually represent one source. And each of them, I mean, because this is three-dimensional, so we are assuming that each source, you know, it will contain three different type of material in different, what should I say, like a percentage. Okay, so we can represent each source in a three-dimensional space. So I mean, if you use all these sources to produce, to mix them up to produce like a material, you can only produce like the you know, the percentage of those different sources inside this polytope. Okay, inside this polytope. That's like I mean, the best you could have. I mean, you just cannot like you know, say we'll add like a, say if you add like a fewer certain source, then it may go to the other end. But you just cannot like, oh, I just get like a negative amount of a certain source. That's just not possible, right? I mean, you can do interpolation. This is basically interpolation, but you cannot do extrapolation, right? Okay, I mean, when you mix up things, I mean, at best, you can just do like, I mean, interpolation. So the interpolation, I mean, geometrically can be interpreted something like this. Okay, so suppose we mix P1, P2 up to Pn in the ratio L1, L2, L up to Ln. Okay, and then L be like capital L be like the summation of Li, and then lambda I be the Li divided by capital L. The mixture we get by mixing the base mixtures in a given ratio is summation lambda I times Pi. So this is like the mathematical formula. But in reality, I mean, this is what we get. Okay, we are going to get a polytope. Polytope. Okay, so the issue is like now, I mean, this problem gives us a motivation to compute a polytope. Okay, so this obviously is convex, right? This shape is convex. And we already know, okay, in two-dimensional situations, for example, like this situation, or if you have just two different material, then what you are going to get is, well, I mean, because you represent all these points on a two-dimensional plane, then what you are going to get is going to be, I mean, when you interpolate all these sources, what you're going to get is a convex hole. Okay, it's a convex hole. So it's like we already know how to do that. But when this problem becomes like more than two-dimensional, okay, say three-dimensional. Let's just focus on three-dimensional, because if it's higher than three-dimensional, you can easily use the concept that we learned in this chapter to deal with that. Okay, so this is like this chapter we are going to deal with like well, convex hole in higher dimension. Okay, but let's fix at three dimension. Okay. So, okay, in three-dimensional space, okay, let's first consider the complexity of the convex hole. Okay, so if we have P points, okay, to be the convex polytope with n vertices, okay, the number of edges of point is at most 3n minus 6, and number of facets, okay, number of facets of P is at most 2n minus 4. Okay, how do we get that? Okay, I mean, first, I mean, for any, pretty much for any polytope. Okay, for example, this is a cube, obviously, right? This is a cube, and we can sort of like extend this cube to be on a two-dimensional space to form, you know, what should I say, like a subdivision. Okay, so this is not just for the cube. This is true. This is the case for any polytope. For any polytope, you can do some experiment. I mean, of course, here I'm not offering you a formal proof of that. Okay, this chapter is, I can tell you, this is the only chapter in this class that the proof is lacking. Okay, we don't have proof because the proof is beyond the scope of this class. It's too difficult. Okay, but I'm going to discuss an interesting algorithm here. Okay, that is also why, I mean, this chapter is much shorter than the other. Okay, so anyway, okay, so first, I mean, for any polytope, you can sort of like you know, map to that to be on a two-dimensional space so that it becomes a subdivision. Okay, so because of that, and if you can check, okay, this mapping not only preserve the number of vertices, number of edges, it also preserve, you know, number of faces. This is very interesting. It also preserve number of faces because this cube has 6 faces, obviously, right? So if you look at here, you have 6 faces too. Okay, 1, 2, 3, 4, 5, 6, the outside face. Okay, so because of that, so we know that, okay, we can apply like the Euler formula, okay, directly here. Okay, so number of vertices, which is n, minus number of edges plus number of faces is 2. So this is directly obtained from Euler formula, and we know, okay, we can estimate the number of degree. Okay, there are 2 ways to estimate the degree. One is 2 times the number of edges. Okay, this is the exact estimate. So obviously, the number of total degree is exactly 2 times the number of edges. Okay, but the other estimate is that for each face, it has at least 3 edges, right? For each face, okay, or it has at least 3 degrees. But think about this. Okay, this is sometimes, I mean, it could be an underestimate, right? Because a face could have more than 3 degrees, right? Okay, so 3 times the number of faces is an underestimate for the total number of degree. Okay, so 2 times NE, it will be greater or equal to 3 times NF. Okay, so based on these 2 formulas, we know, okay, the given n vertex, the number of edges of P, this P is a polytope, is at the most 3n minus 6, and number of faces of P is at most 2n minus 6. 2n minus 4, I'm sorry. So the most important thing we know here is that the complexity of the convex hull of a set of n points in 3-dimensional space. Here, I'm talking about this n points. Some points could appear inside the polytope. I'm talking about arbitrary n point, and I'm trying to use this arbitrary n point in 3-dimensional to create a polytope. Think about this. because some points are inside the polytope, right? Could be inside the polytope. So the total number of vertices of the polytope will be smaller or equal to n, right? Will be smaller or equal to n because some points will be inside the polytope, which wouldn't be considered as a vertex in the polytope, right? Okay, so we know, okay, I mean the complexity, I mean here of the convex hull, I'm talking about the number of edges and number of faces are both linear to, bounded by the linear of by the linear of the n. Okay, linear function of n. Okay, so that's like just want to give you an idea. Okay, and then, okay, how do we create a convex polytope? So here is an interesting idea. Okay. In this chapter, we are going to talk about an algorithm. This is, again, a randomized incremental algorithm. So we are going to add one point at a time in random order. Okay? So assume you already have a polytope. Okay? So this is the polytope that you originally have already. Okay? And then now you want to add a new point into this polytope. Okay? So if that new point PR that you want to insert happens to lie inside this CHPR minus 1 means like the polytope, the convex hull or convex polytope that you have created by P1, P2 up to PR minus 1. Okay? So if this PR lies inside this polytope, okay, or on the boundary, then CHPR will be CHPR minus 1, right? It will be the same, right? Adding this point, the resulting polytope will not change, right? Because if it appears inside the polytope or on the surface of polytope, then pretty much adding this point will not change the shape of this polytope, right? Okay, so this is, if you think this is obviously the case, right? Just kind of like, in a two-dimensional case, okay? If you have a convex hull, now you add a new point inside the convex hull, it wouldn't change the convex hull at all, right? So now, okay, if this is not the case, if this point is outside, then it will be very interesting. It will be very interesting. Okay? How do you add this point? This is PR. It is outside of this polytope. Okay? You could imagine, okay, your eyes here, you are looking at this polytope. Okay, the faces that you can see will no longer be included, okay, after you insert PR. And you are going to, actually you are going to see your boundary, kind of like a boundary, two-dimensional boundary. I'm not talking about three-dimensional. It's kind of like we call that like horizon. We call that horizon. Okay, just like the boundary. Okay, just when you look at this, okay, I know a lot of you like to play computer game, right? Okay, computer game. A lot of you talk about like 光追, right? 光追. Okay, 光追 is actually ray tracing. Okay, ray tracing is something like this. Okay, you just use from this point. Okay, you just draw a line that go past. So draw a line, okay, that you know go to that direction, and you will see that, okay, this the boundary actually can be obtained. Okay, of course you are not going to get the boundary like that, but I'm just telling you, okay, you can identify the boundary, you know, conceptually like that. Okay, and then you can just add, after you delete the faces that that are visible to you, then you just add this boundary, these faces, one by one, to this polytope, and then you finish the insertion. Okay, so you can see that, okay, the result is going to be something like this. From CHPR minus 1 to CHPR, assuming PR is outside of the polytope. Okay, very interesting, very interesting. Okay, so obviously, you can see that, okay, the ability to compute, okay, whether a point is, you know, whether a facet is visible by PR, by another point, is very important here. Okay, you need to be able to compute that, whether a facet is visible or not by a point. Okay, so previously I just told you, okay, the polytope, okay, you can extend the polytope to two-dimensional, and that will become subdivision, right? So we could actually, okay, in the data structure that we use to store polytope, we actually could just use the data structure that is used to store the subdivision, okay, which is a doubly connected edge list. Okay, we actually really use the doubly connected edge list data structure to store the polytope. Okay, and we say F is visible from P, okay, here. For a facet, okay, you can see that, okay, it has two sides, right? One side is facing outward. One side is like is where the polytope is located. So you can see that if a point P is on the opposite side of the polytope, then P will be able to see F, okay, or you can say F is visible from P, okay, but it will not be visible from the point that is on the same side of polytope, okay. So this is very important. Okay. So I already told you how to consider adding a point PR outside of the polytope. So it's not difficult, but okay. So we need to find the visible faces. In order to be able to add a point that is outside of polytope efficiently, we need to be able to find what should we say, like a visible faces very efficiently, right? Okay. So testing every facet in CHPR minus 1 to see if it is visible to PR. Okay, it takes big O the number of facets in CHPR R minus 1. Okay, so this is like a number of facets. Remember, previously we just say like this is like a linear. This is linear to R minus 1, right? Okay, so if you do not do anything to optimize that, then the complexity of convex hull construction using this manner, okay, say like we check every facet to see if they are visible from this newly inserted point. Okay, every time we do this, then it's going to result in big O n squared. Okay, well, we don't think it's good enough. It's not good enough. Okay, so far, almost all the algorithm we talk about, like the time complexity will be cheaper than n squared, right? Almost every algorithm we discussed. Okay, so we consider n squared actually expensive. Okay, expensive. So how do we get this job done much more efficiently? Okay, we have a way to do it. Okay, but sadly, I can only I can tell you the idea, but to prove the complexity of this algorithm is cheaper than n squared is beyond the scope. Okay, actually, like if you are interested, I mean, this is which chapter? Chapter 14 or chapter 12? I forgot. Okay, I mean, you guys can check out like the advanced section. I mean, to learn how to do the analysis. Okay, of this algorithm. But as I say, like this complexity analysis is out of scope. Okay, so the idea is we can maintain a conflict graph G, which is a bipartite graph, okay, consisting of conflicting points and the corresponding conflicting faces. Okay, so what is this conflict graph? Let me explain here. Okay, let's say up to now we have constructed a polytope of r-1 points. Okay, we already have a CHP r-1, meaning we already inserted P1, P2, P3 up to PR-1 to create a polytope. Okay, and the point set. Okay, this part is the point set. The point set contains the points to be added at a later time. Okay, so these are the points to be added later. So, which include PR, PR plus 1, PR plus 2, blah blah blah, to Pn. Okay? So you could imagine at the very beginning, these points, you have a lot of points, right? I mean, up to n points, obviously, right? Okay. Huh? What happens? Auto battery. How come? 奇怪，发生什么事情？是不是这个电被拔掉了？完全没有，好像没有充哎。哎，我的 laptop 可能也要换了，要不然连3堂课都撑不住。你看，就是写说没有电啊，奇怪，怎么会这样子？啊，它现在是没有充电的。对啊，这个现在是没有电的。我没有嘞，就是这条线是好的啊，原来是好的啊，奇怪。里面也没有别的，等一下。 奇怪，为什么会这样子？这边有问题啊！好，试试看，试试看。不够长吗？没关系。没有，还是没有。唉 ，Our school is poor. Maybe they forget to pay for the electricity. I don't know. 这到底现在，好像，刚。到目前为止都好像不 work 啊，奇怪了，怎么回事？不可能，不可能，这个 laptop 还没有到这种程度啊。Okay, it's okay. Well, that's fine. I guess like we wouldn't be able to finish this chapter anyway, because technical difficulty. Yeah. Yeah. I don't know why. I mean, my laptop died on me. 不行，没办法。Yeah, I mean, yeah, we will finish this chapter. Well, it actually should take less than another 10 to 15 minutes to finish it. Unfortunately, I mean, we couldn't get it done today. But well, let's do it next time. Okay, we have probably less than another 3-4 slides to go. So, but I will have the homework 4 uploaded. Okay, today. Originally, I wanted to finish this chapter so that like homework 4 cover the line triangulation and this convex hole. But since we will finish this chapter like next time, maybe another 10-15 minutes. So, and the due date of this homework 4 will be 2 weeks from today anyway. So I think, I mean, I would just, remind you like I already have the homework 4 uploaded. Okay? Yeah. I mean, you can start working on that, I mean, early. Okay? But for this chapter, well, unfortunately, maybe, I mean, you start working on it like next week after we finish this chapter. Yeah. I'm sorry to tell you that. I mean, I don't know. Anyway.
Most of us start the work 1 week later anyway.
Oh, really? Yeah. I mean, actually, you guys should have started earlier. Okay. I mean, it's not a good sign. Okay. Okay. Anyway, so well, I'm sorry about that. I mean, we wasted like 10 more minutes, like just because of this technical difficulty. Yeah. Well, sorry. So let's talk again next week.